Hi everyone, I'm Etienne Chauchot and I'm gonna give you fresh updates about the new Beam runner based on Spark structure streaming framework. This talk is a continuation of the talk I gave last year at the ApacheCon to present the building of this new runner. And it belongs to the big data track, even though it was put in the streaming track. Let me introduce myself. I'm a software engineer at Talend, and I'm an Apache Beam committer and PMC member. I'm also contributing to Apache Flink and a bit to Apache Spark. You can catch me on Twitter, by email, or with my blog. At Talend, we do data integration software. In that case, the screenshot is Pipeline Designer. It's a tool that allows to build big data pipelines by assembling UI components, and it's based on Beam. So this is the agenda for today. I will start with an introduction to Beam for those who don't know it. I will then do a very brief introduction to Spark Structure Streaming Framework. I will then give you the overall Beam runner architecture so that you could know what a runner is. I will then switch to latest improvements in terms of features. I will then dig into a problem that we have with the Spark Structure Streaming Framework. And I will then give updates on performances and a conclusion. So as an introduction to Beam, I will just give this quote. Beam is a programming model that allows to create big data pipelines, and it's unified between batch and streaming with a unified API, I mean. So that's because we believe that there is no real difference between a batch pipeline and a streaming pipeline. The only difference is that the streaming pipeline deals with an infinite collection of data, whereas the batch pipeline deals with a finite collection of data. And all you need to do is to divide this infinite data into finite chunks. So the overall batch problem can be seen as a subset of the streaming problem. And to divide the data, all you need is windowing, and Beam provides it. That's the Beam stack. On top of it, you have the user code. So that's the pipeline written by the user using the libraries of transforms and the IOs that are provided by the language SDKs. There are several language SDKs, one for Java, one for Python, one for Go, and they all expose the Beam model concepts like windowing. We will see that later on. And the bottom layer is the focus of interest of this talk. It's the translation layer between a pipeline written with the Beam API and a native pipeline for Spark, for Flink, for data flow that will be executed by the actual engine. The Beam transforms, actually there are only 3 Beam transforms, 3 primitives. There's the Pardo, which is the good old flat map that is basically an event-wise processing, an element-wise processing, sorry, and the group by key, which is a way to group elements into groups that could be later on processed in parallel downstream the pipeline. And there is the read that is there to ingest data into the pipeline. All the other transforms available in the Beam SDKs are composites of Pardo and group by key. Even the reducer equivalent, which is called combine in Beam, is implemented by Beam SDK as a Pardo and a group by key. This is the traditional, usual example, very straight, very simple pipeline that reads text file, counts the occurrences of the words, and prints the output to a text file. It is there just to show you the Beam API. So we have the pipeline, which is the user interaction with the pipeline. We have the P collection object, which is an abstraction of the data spread across the cluster. We have several transforms, flat map, count, map elements, and text IO that allows to read from text file and write to text file. So this slide is the Beam vision. It's to say that you can write your pipeline using whatever language SDK, in Java, Python, or Go, and run it on any big data engine that is supported, no matter what the language was used to write it. For example, you can write a Python pipeline and run it on Spark, which is coded in Scala. So this is quite out of the scope of this talk because it's portability. It will be dealt with tomorrow, but by Alexei Romanenko, but I needed to mention it. So this is the first model concept of Beam, which is windowing. Windowing is a way to temporarily group elements based on their event timestamp, the timestamp at which the element occurred. And it's mandatory for streaming because you need to divide the infinite data, as I said before, but it's optional for batch mode, because even in batch mode, you can set your timestamp on your data and still apply windowing. We have several types of windows. We have the fixed windows that allows to express things like, I want to have the last 30 seconds of data. We have the sliding windows that allow to express things like, I want to have the last 60 seconds of data every 30 seconds. We also have the session windows that are very similar to web session, meaning that they are defined by a gap duration. So let's say we have a 30 seconds gap duration set. If we receive no elements for more than 30 seconds in event time, then the next element will be considered as belonging to the next session. We also provide two special kind of windows. The global window, which is the default one, the one you get when you don't specify your window. That's the window that contains all the elements in batch mode, all the elements of the pipeline, of course. And we also have a special custom window that is basically the way for the user to specify for a given element based on its timestamp to what window it should belong. So that's a function to implement for the user. Another very, very important concept of Beam is watermarks. We will deal with that later on, but I need to say that for the watermarks, that for all the streaming systems, we always have problems like lag between the event timestamp, so it's the time at which the element occurred, and the processing time, which is the time at which the element was processed by the system. And we also have out-of-order data. And to deal with those 2 points, we provide what we call a watermark. A watermark is a point in time where we should not receive older elements. In other words, it's the system notion that all the data for a certain window is expected to have arrived, to have come in the pipeline. So if I take a very simple example, very naive, of a 10-minute lag watermark, very static watermark, at 2:10, the system will consider that no element with timestamp older than 2 o'clock can arrive. So it's a lag of 10 minutes watermark. The watermark is set by the source, and it's propagated throughout the pipeline through the different transforms. And a corollary to that is late data. Late data is data that arrives after the watermark. So if I take my previous example of this simple 10 minutes lag watermark, for a given element, if it has a timestamp of 1:59 and it arrives at 2:11, then as at 2:10 the watermark will consider that no elements older than 2 can arrive, then this element with timestamp 1:59 will be considered late, and it will be dropped unless we set what we call a load lateness, and a load lateness is a tolerance in time, and in that case it avoids the element dropping. So for the previous example of this element with timestamp 1:59, to avoid that it's dropped, you need to set a load lateness of at least 2 minutes. Another model concept important is triggering. Triggering is what tells Beam when to output data. The default trigger is when the watermark pass the end of the window. So with my previous naive static watermark example of 10 minutes lag, a given fixed window of 1 hour from 1 to 2 will be closed at 2:10, because at 2:10 the watermark value will be 2 o'clock and it will pass the end of the window. So that's when the output will come and the buffers will be cleaned and all these things, and in the data output. There are several types of triggers: event-based triggers, event time-based triggers based on timestamp of elements, processing time triggers that are based on the time at which the element was seen or processed by the system, and data-driven triggers that are based on the count of elements. But we also can have early triggers that emit data before the window closes. It's useful for preview, and also late data triggers that emit their data after the watermark has passed the end of the window. I will now do a very quick introduction to the Spark structure streaming framework. It's a framework that was released in beta with Spark 2.0 in July 16. It's based on Spark SQL, and it provides an API unified for batch and streaming that is called dataset or data frame. It has a type and a schema enforcement. You actually define the structure of your data, and it gets enforced by the framework, but it's still micro-batched. Even though they defined the continuous processing mode that is not micro-batched and that is available for low latency pipelines, this mode does not support aggregation in streaming at all. You cannot do a group by with the continuous processing mode. So it's not useful for Beam, because obviously we need to do aggregations. It has also an optimizer that is called Catalyst, that is very similar to a SQL optimizer. Its job is to optimize the execution plan of the Spark queries. So that will be all for the Spark introduction. I will dig into the subject of the Beam runner itself. So you remember the pipeline I gave in the introduction, the very simple one that reads text file. Actually, this example, this pipeline will result when the SDK will pass it. The SDK will construct a graph such as this one on the right-hand side of the screen. It's the direct acyclic graph. So the short is DAG. It contains only beam transforms, so read, flat map, count, map elements, and write. And this is what is used as an input for the runner translation. The job of the runner is to translate this DAG to the native pipeline code that you see on the right-hand side. Of course, it's pseudocode, but you see that it's native Spark because there is backsession, read, data source v2, flat map, and all these things. And this is this actual native pipeline that will be run in the Spark cluster. And let's take a look at the left-hand side for a bit. You remember that I said in the introduction that there were only a few primitives in Beam. So read is a primitive, but flat map is not. Flat map is implemented in the SDK as a pardo. Count is not a primitive either. It's implemented as a Beam combine, which is itself not a primitive. As I said before, it's implemented in the SDK as a group by key and a pardo. And map elements is a pardo and write is a pardo. What happens there is that the runner job is to translate, so it will visit this tag, but it can choose the level of translation. It's the object of these green boxes. For the read, there's no point because it's a primitive, so it gets directly translated to a Spark read with data source v2 API. And the pardo is translated as a Spark flat map. But where it's interesting is with the combine, because with the combine, we could have chosen to translate the Beam group by key to a Spark group by key and a Pardue to a Spark flat map, but it would have been less performant than directly translating the Beam combine to a Spark aggregator, because they are equivalent. So that is more performant to do the translation at that level. So when the runner visits this DAG, it creates an input dataset as a result of the read, stores this dataset, and applies it, the first transform, stores the output dataset, and use it as an input for next step, and so on and so on and so on, until we reach the output dataset. That will be the final dataset of the pipeline, and we will apply to it an action. In that case, it will be a for each action, because it's a batch pipeline. So now, how do you run this pipeline with this new runner? You simply replace the -- runner equals Spark runner in Beam command line by -- runner equals Spark social streaming runner, and you will get an output such as this. In that case, it's a very simple example of a Pardue that is executed on data. And this screenshot is the output of Catalyst. It's the physical plan that is actually executed by the Spark engine. So it's readable from bottom to top. So you can see it starts with a source in batch mode. It then applies the binary schema defined. The source creates row, so it deserializes to row. And then we with a map element deserialized to window value, because window value is the object that the Beam pipeline deal with in the inside. It's window plus data. And we then apply the Pardue that is defined by the user in the Beam pipeline. And after that, it's the result is reserialized to bytes, so that Spark could deal with the data for downstream the pipeline. I will now give you the latest improvements in case you already tested this Spark runner. There were some minor fixes, like the flatten. The flatten is a merge of two P collection, and it now works on empty P collections. We also avoided staging of the jars in Spark local mode, because in this mode, the Spark engine runs inside the same JVM, so there is already the libs in the class path, so we don't need to stage the jars. We also improved the pipeline options by splitting them between the current RDDD streams based runner options and the structure streaming based for the structure streaming runner options. And we introduced the test mode that you saw in the previous slides. The log that you saw is the test mode output for the execution plans of Spark. And we also fixed the materialization in batch mode, because at the end, Spark needs to materialize data, and for that, it needs to apply an action to the output dataset. So in batch, we chose to apply the for each. We did also a good amount of work on the combine translation. So as I said, the combine in Beam is the equivalent of reduce in big data. Let's say that we have a cluster with 3 executors. So as I said, the P collection is spread across the cluster, so it's divided into 3. And for each executor, Beam creates an accumulator, a local accumulator, to which the data of the local part of the P collection get added. And then the accumulators get merged between each other into a single accumulator that resides on a single executor. And it's accumulator that gets extracted to produce the output data. So what's important in that is that you saw in the introduction that we have complex windowing. For that, we cannot rely on Spark windowing. We use our own windowing with the windowed value that you saw in the logs. that contains windowing information. So as a consequence, when we merge the data in the accumulators, we need to merge by the windows. So we need to merge the accumulators by their target windows and the data as well. So it's important to know that we had a lot of work to deal with window merging. There is also now the sliding window type that is support, and there were minor fixes on timestamp and instance reuse. Instance reuse because Beam tries to spare as less memory as possible, so it reuses instances of the accumulators, and we need proper reinitialization. We also now support beam coders. What are beam coders? Beam coder is simply a serializer deserializer. It's an interface. So they encode for serialization of an element to a bytes array and decode for the deserialization of this byte array to the element. These coders are either provided by the user, which just implements this interface, and it can be also provided by the SDK. So the SDK provides several coders, beam coders for several types. And these coders are very, very similar to Spark encoders. But before talking about Spark encoders, I will just do a quick parenthesis on the catalyst optimizer, Spark catalyst optimizer. Like I said before, it's similar to a SQL optimizer. Its job is to iteratively apply rules to the user DAG to generate at the end the best physical plan possible. So it iteratively applies rules to end up with that. And Catalyst sees the input pipeline as a tree made of tree nodes. And there is a special kind of tree nodes that is called catalyst expressions. And there is a special type of catalyst expressions that are expression encoders. And those expression encoders are actually custom Spark encoders. And that's what we used to wire up, to wrap the beam coders into a custom Spark encoders as an expression encoder. But what's important to notice there is that all catalyst expressions generate Java code. Actually, they generate strings of Java, and these strings of Java are compiled by the Janino compiler at the Spark side when Catalyst processes them. And this is this code, these Java strings that call the beam coder. So what's the current state of this new runner? It was merged to Beam Master. It covers 100% of the Beam core features. There is still optional features that are not yet implemented, like the state API, like the timer API, like the splittable doFn API, and also side input in Combine are an ongoing work. The Beam schemas are not wired up with Spark schemas. We use for now Spark binary schemas. Also, the runner can execute nextmark in batch mode. So what is nextmark? Nextmark is our internal Beam performance framework that covers 100% of the model, and that simulates an auction system. It simulates persons creating auctions, placing bids on items, and then it queries the system for statistical data, such as what's the average selling price in the United States. And these queries are actually Beam pipelines. This runner is only in batch mode, only available in batch mode, because the streaming mode is not supported yet, because we have a problem with the Spark structure streaming framework, which is at the Spark side. That will be the focus of next part. So the multiple aggregation problem in Spark structure streaming framework. The problem is that this framework does not support multiple aggregation. It does not support more than one aggregation in a streaming pipeline. So there's an open ticket, and there is also an ongoing PR, but it has not received an update since August 19. And there's also an ongoing Spark design, but that received no update since June 19. So the Beam project is stuck with the new runner based on Spark structure streaming framework, waiting for the support for more than one aggregation in a streaming mode. So what's the underlying problem that is at the Spark side? Actually, the problem is the watermark scope in Spark. This scope is global for the whole pipeline. There is no watermark per operation. And how it works is that at the end of each microbatch, the watermark is updated with the newest timestamp received. So if I take an example like below, a streaming pipeline with 2 aggregations in a row, so that's not supported. We will see how it doesn't work. So there is the first aggregation that outputs the highest value in the window of 3 seconds. So let's say that we receive 3 elements with value 6, 4, and 5, and timestamp 1, 2, and 3. So they get buffered in the operation 1. The operation 1 updates the global watermark to value 3 because it's the newest timestamp seen. So as a result, when the operation 1 outputs its data, no luck, the highest is value 6, but it has timestamp 1. And as the global watermark is value 3, then this element with timestamp 1 will be considered by operation 2 as late. So then it will be dropped, and this will lead to incorrect results. So as a consequence, to avoid incorrect results, then the Spark project deactivate the support of more than one aggregation in streaming pipeline with this structured streaming framework. A possible solution that we discussed with the Spark community is to replace this global watermark by watermarks per transform. And these watermark values will be propagated through the pipeline from the source throughout the different Spark operations. And each operation will update their local watermark as they receive data. And we define for each of these operations an input watermark, which is defined as the minimum of the output watermark of the previous operations. Of course, this minimum is only for Y pipelines. If you have a straight pipeline, then the input watermark is the minimum of the output is directly the output watermark of the previous step. And the output watermark is the minimum between the local input watermark and the oldest processed. So let's say now in an example how it works. So we take the very same example like before, only this time we define a watermark per operation. So there is one for the source, there is one for operation 1 and one for operation 2. And also, let's say that the source at some point says that the watermark is 1, meaning that we should not receive older element than timestamp 1. This watermark gets propagated through the operations, like I said. So the input watermark of operation 1 is the output watermark of previous step, so it's 1. The output watermark of operation 1 is the minimum between the oldest processed and the input watermark, so it's 1. And for operation 2, the input watermark is the output watermark of previous step, so it's 1. And the output watermark of operation 2 is the minimum between the oldest processed and the local input watermark, so it's 1. So let's say now that we receive the very same 3 elements with value 6, 4, and 5 and timestamp 1, 2, and 3. So they get buffered inside operation 1. So the operation 1 updates its current oldest processed counter to the oldest timestamp because it's the oldest process counter, so it's timestamp 1. So it does not update its output watermark because the output watermark is the minimum between the input watermark and the oldest process, so it's still 1. So if the output watermark of operation 1 is not updated, then the input and output watermark of operation 2 will not be updated either. So now let's say that the source says now that the watermark is 3, meaning that we should not receive all the elements that timestamp 3. What happens is that this watermark is propagated to the input watermark of operation 1. And now something interesting happens, because the input watermark of operation 1 is value 3. So the watermark has passed the end of the window. So if you remember what I said on the triggers, then the watermark has passed the end of the window of 3 seconds. So it should output its data. So operation 1 should output its data. So it will do so. So cleans this buffer, outputs its data. So it will output, as before, the value 6 timestamp 1. But now, as the watermark is local, the input watermark of operation 2 has not changed, it's still 1. This element with timestamp 1 is no more considered late, and it will not be dropped. It will just be buffered and processed. So operation 2 will just update its current processed counter to 1. And now you may wonder, when do these watermarks get updated? Well, let's say we receive another element with timestamp 4 with value 7. It gets buffered in operation 1. So this time the operation 1 updates its oldest process counter to 4. So now 4 is higher than 3. So the output watermark, which is the minimum between the two, gets updated to 3. So as the output watermark of operation 1 is updated, then the input watermark of operation 2 will be updated to its value. So it will be now 3. And the local output watermark of operation 2 will be also updated to 3. So now you know how could the watermark be updated with the arrival of value and throughout the operations. I will now give updates about the performances of the new runner. Well, what do we do for performances? Actually, we schedule load tests per transform on a schedule basis. We also run nextmark on each commit on master to follow the performance of the runner. And we also did some profiling on the nextmark queries to spot places to improve. And as a development process, we also, for each new change, run load tests to ensure that there is no performance regression. So it led to some improvements, but also some failures. So the improvements brought by the beam coders, previously, before being compatible with beam coders, we used cryo encoders that are generic encoders, the generic Spark encoders to serialize data, and we replaced it by the things I presented, and it gained 40% in execution time. For that, we minimized the generated code, so we used as much JDK compiled code and as little Janino compiled code. You remember the Java strings I mentioned? For the group by key, we managed to remove an internal Beam flat map in the translation from Beam to Spark, and it gained 20%. We also are refactoring right now the combined Beam translation to support side inputs. So what are side inputs? Beam side inputs are like a view on a P collection, and this view can be injected to a transform, combined in that case. So it could be useful for something like a reference table that you want to cross with data coming to a combine, for example. And these stem views actually right now use broadcast variables. And to use Spark broadcast variables, you need to serialize data. So you need to materialize your data to set the broad course variable. And this could have been avoided. We could have been avoided materializing the data by using Spark temp views. And Spark temp views are like SQL views. Sorry, they can be cached and they can be also lazily evaluated. And it could have been then a better performance candidate for the Beam side input translation. And it has failed because Spark SQL context cannot be passed to a map because it is not serializable. So we cannot use temp views to translate the Beam side inputs. So we stuck to broad course variables. Updated performance. This performance chart is the execution time of the nextmark queries. So there are 14 of them. So you remember nextmark is the simulation of the auction system, and the queries are, let's say, statistical questions on the system. It's a run that was done on 100,000 events with, let's say, a local Spark of 4 threads. And we see in blue the execution time of each query, in blue for the new Spark runner based on Spark Structured Streaming Framework, and in red the response time for the current Spark runner based on RDD and dstring. And you can see that in some places the new runner behaves better than the current one, because the bars are lower. In other places, they behave similarly, like in query number 0 or 1. And in some cases, the new runner is worse in performance than the current runner. That could be explained by the fact that there was a lot more performance improvement on the current RDD dstream runner, because it is still considered by the Beam community as the main Spark runner. Also, that can be explained by the use of binary schemas in this new runner. As a consequence, Catalyst cannot do some optimizations. The optimizations that are based on fields, as it sees only a bytes array, it cannot do field-based optimizations. And also another thing is that as we use binary schemas, we serialize the whole content of data. And in some cases, we could have serialized only one field. So it could have been quarter performance in that case. So I will jump to the conclusion. As a conclusion, I will just say that contributions are welcome. Also, feel free to join the Spark Runner Beam channel, and also take a look at the Apache Beam website. You can join the Beam mailing list. You can follow us on the Beam handle. And also, if you need some more details on some of the topics of the talk, you can take a look at my previous talks. The first one on the Spark Structured Streaming Framework runner that explains the building. You can also take a look at this nextmark talk. And if you need some more details on the Spark encoders, you can take a look at the blog I wrote on this topic. I will also say that my friend Alexey Romanenko will present a talk tomorrow about portability. So that's cross-language pipelines. So I urge you to take a look at his session. If you have some questions, I am a bit late. I maybe can take one question. Is it possible to estimate the hover rate of Beam using Structured Spark versus native Structured Spark performance? Well, very good question. Actually, as far as I know, this overhead was never measured. A good way to do so will be to pick up some of the more important nextmark queries and recode them using Spark native and compare the response time of the two with the runner with the native pipeline. But what I can say, I don't have figures to show, but what I can say is that when Beam executes pipeline.run, it does first the translation that I presented in the architecture, and then when the native pipeline that I showed in the native Spark is produced, then it's that is run in the Spark engine itself. So there is no more Beam at that point. Of course, there are still the wrappers to call Beam code, but no more translation. And you must know that we try to use as minimum wrappers to reduce memory, as minimal wrappers as possible. We also use as minimum internal steps, like in the Beam translation, forcing a serialization. We try not to do so, not to have these internal steps. And we also tried to be as native as possible. Like I said in the architecture part, with the combined translation, that is more performant to, let's say, translate at the combined level rather than translating the group by key, the inner group by key with a Spark group by key and the inner Pardue with a Spark flat map. It is more performant to use the native Spark aggregator to translate the Beam combine. So that's it. I hope I've answered your question. I'm late by a minute, so I will give a big thanks for joining. Thank you for attending the talk, and see you around in the conference.